Welcome to Lab 4. In this lab we are going to build an adder-subtractor module. So we are first going to take a quick look at the solution for the last lab where you were asked to build a 4x1 multiplexer using basic gates. And the solution to that lab is going to motivate our study of two useful constructs offered by VHDL for creating regular structures. Okay, one is called generics for writing a parameterized description, and the second one is called generate. We are going to use these two constructs that we learned for VHDL to solve our exercise. So the first question in the exercise for lab 4 asks you to build an n-bit triple carry adder. Remember, in lab 2 you were asked to build a 4-bit triple carry adder, and you will be asked to generalize that description to an n-bit adder using these two features of VHDL. Okay. In the next question, we will use that n-bit triple carry adder as a component along with some other components such as a multiplexer to build a hardware that can be used for both addition or subtraction of signed numbers. Okay, so let's get started. So this is the first question in lab 3. You were asked to build a 4x1 multiplexer. It has 4 inputs A, B, C, D, 2 select lines for selecting one of these inputs and the output. And this is the circuit. So essentially to the first AND gate we connect S1 bar, S0 bar. To the second one we connect S1 bar, S0, then S1, S0 bar and S1, S0. And the third input to each AND gate is the input to the mux A, B, C, D, right? So for example, when S1, S0 takes the value 1, 0, then this S1 is 0, this both inputs are 1 and this gate is enabled. Outputs of all the other AND gates are 0. This is enabled and whatever is the value of C propagates to the output Y. So Y is equal to C. So in this way we can use the two-level AND OR structure to act as a multiplexer. So here is the circuit. Let's see how to describe this in VHDL. So we first have the descriptions for the entity and architecture descriptions for the 3-input AND gate, the 4-input OR gate and the NOT gate. This is straightforward. And we shall use these as components to build a 4x1 mux. So first we describe the interface for the 4x1 mux, which has these 4 codes. The S select lines, which is a standard logic vector, and the output Y. We then declare these components, the 3-input AND gate, the 4-input OR gate, the NOT gate. Okay, and then we need to have some additional signals for the intermediate values for interconnecting these gates. So first we need to have complemented values of S1 and S0. So we declare a vector called not S, where not S1 is a complement of S1 and so on. Okay, and we have 4 signals which are inputs to the OR gate. Okay, we initialize them to all zeros. Okay, so now let's start. We first instantiate the 2 NOT gates, and the inputs are S0 and S1 and outputs are not S0 and not S1. And then we have these 4 AND gates. So these 4 AND gates, to which go the inputs A, B, C, D and these 2 select lines, either their complement versions or the original version. So we connect them this way. Okay, and each of their output goes to the OR in lines, and finally all of these are connected to the OR gate, 4-input OR gate, whose output goes to Y. So this is a straightforward description, but now this serves as a motivation to study the two useful features of VHDL. The motivation is that, remember, if you had to describe a more complicated circuit structurally, for example, if n was, let's say, 128, that would end up causing a lot of repetitions here in this structure, right? And that is also prone to errors. What if you made a mistake in one of these things? It's prone to errors. So so what if there was a way to automate writing such things? Some kind of a for loop which would allow you to create these regular structures. So that's exactly what the next 2 features allow us to do. Okay. So the first feature we are going to see is called generics. So this offers a way to write a parameterized description. Okay. For example, imagine you had a circuit in which you had a 2 input AND gate and a 3 input AND gate and a 4 input AND gate and a 5 input AND gate, for example. Now, instead of having to write these descriptions for each of these gates 5 times, maybe you could write a description for an n input AND gate once, and when instantiating a component of this type, you could describe or specify the value of n. That's exactly what generics allows us to do, among other things. Okay, so what it allows us to do is to specify a parameter n, write the description in terms of n, and then you could specify the actual value of n at the time of instantiating a component. So we see an example of the AND gate now. Let's write description for an n input AND gate. So this is how you do it. You say AND gate is, then we have generic n of type integer, and then we have port. Okay, so we want an AND gate which has one output y and inputs x0 all the way to xn minus 1. Okay, so this is what we want. So we declare the generic this way: generic n, currently it's of type integer, it can be of other types, and then we define the size of the AND gate with respect to n. So x is a vector of size n minus 1 down to 0. Okay, now how do we instantiate such a component? So here is a test bench. Okay, and here we are going to instantiate a component. So first we declare the component as it is. Component AND gate is, again, this is just a copy of these two lines. Okay, this is a signal S to connect to this gate, of course. Okay, in the test bench, and you connect Y again to another signal called Y in the test bench. Okay, and we generate a component, instantiate a component A1 of type AND gate, and just like there is port map, we have generic map where n is assigned the value of 3. So this is going to create a 3 input AND gate, and we are going to map S to the input x and y to input y. So S is already a vector of size 3. Okay, and then we apply some signals at some waveform at S. So notice that in addition to the port declaration, generic is also a kind of an interface of the module, right? So an interface is basically what is the name of this entity, what are its input and output ports, and what are the parameters that it takes. For example, n is also a parameter. So this entire interface description is written within the entity block. This also includes the generic statement. Okay, so this generic declaration tells what are the parameters of this entity, and when you are actually instantiating an object of this type, you have to specify the value of n. Okay, that's fine. Now we have not seen what is the architecture of this AND gate, right? How do you describe the behavior of the AND gate in a generic way with respect to the parameter n? Essentially, y is 1 only when all the values of x are 1, hence it is 0. That's what we want to describe, correct? So we have to write a generic description with respect to the parameter n. So how do we do that? So here is a full description of the AND gate. So we can use the conditional assignment. Okay, remember this from the last lab. Y is assigned the value 1 when x is all ones. That means x is equal to a vector n minus 1 down to 0 of all ones. This syntax actually creates a vector of all ones of size n, this one statement, and if x is equal to that, then y is assigned a value 1, else it is 0. So this is one way of writing the description, a behavioral description of this AND gate. So this syntax is generally generic, the name of the parameter and the type of the parameter. So far we have only seen one type, which is called integer. Let's see another type of the generic parameter. It can be of other types. So for example, here is an AND gate. It has two parameters. One is n of type integer with a default value of 2. Okay, so you can assign a default value also to this parameter. What happens is when you create a component of this AND gate but you fail to specify n, you do not specify a value of n, then the default value is taken. So if you create an AND gate, you don't specify n, then it will be automatically assigned a value of 2. But if you pass a value n equal to 3, for example, it will create a 3 input AND gate. So this is the default value which should be assigned when you don't specify it. It has another parameter delay, okay, of type time. This is a valid type and the default value is 10 nanoseconds. So we construct an AND gate with n inputs, 1 output, and that gate has a delay. So what we have is, we have this n inputs and the output y, and we declare an intermediate signal here called output, which is actually assigned to y. So output is 1 when all the inputs are 1, just like in the previous example, and y is assigned the value of output after delay. So there is some delay associated with this gate. Okay, note that this is not a synthesizable VHDL code because there is this after delay construct. This is not a synthesizable element, but it's a valid description for simulation. So this is a simulation waveform. You have x, okay, the vector x, and the 3 input AND gate. So there is a vector of size 3 bits, and output is 1 only when all 3 are 1. So at 7 this is 1, and y is equal to output but delayed by 10 nanoseconds. So you can see this, it's a delayed version, and right at the beginning this is undefined. Okay, this is undefined. This is the notation for undefined in VHDL. So that's because in the beginning this is not initialized. Okay, y is not initialized, OP is initialized but y is not initialized, so it takes an undefined value. So this kind of a thing helps us to identify where we have not initialized some output values and so on. Alright. So let's write a generic description of a mux using this generics feature. Okay, we want to describe a mux in a behavioral manner with n inputs. Okay, sorry, with inputs of size n. There's a difference. Okay, so we still are describing a 4 input mux with inputs a, b, c, d, and an output y and 2 select lines S1 and S0, but each of these inputs is now of n bits and the output is also of n bits. So for example, when S is 0, 0, all of the bits of A are connected to the corresponding bits of Y. So Y takes the value of this whole bunch A. Similarly, when S is 0, 1, Y is equal to B, and so on. This is the mux that we are creating, where n can be anything. We write a general description in terms of n. Okay, so let's see the behavioral description. We have generic n, which is of type integer. N is the bit width of each input. You still have 4 inputs and 2 select lines, but each of the inputs are standard logic vectors of size n, and y is also a standard logic vector of size n. Okay, and now here is a behavioral description. We are using the selected assignment statement. So with S select, y is assigned A when 0, 0, 0, 1 and so on. This is exactly the same, and the default case it's assigned all zeros. Okay, so this is the behavioral description. This may not occur, right? But it's better to have a default clause in any case, because if we miss out some clause, it could act as a memory element. So it's good idea to list all the options and in addition also have a default clause. Okay. Okay, so in this example, what was our parameter n? It was the width of each input, but we still had a 4 input mux, right? 4 cross 1 mux. What if we want to create a n cross m or a m cross 1 mux? The parameter is the number of inputs. So if we had some m inputs, how many select lines do we need to have? We need to have log to the base 2 of m select lines, right? So to make it simple, let's call this k, the width of the select lines, and so this is 2 to the power k. Number of inputs is 2 to the power k. So let's create such a mux where now the parameter k refers to the number of select lines. So let's make a 2 to the power k input mux using generics, okay, where k is the number of select lines. So we have a generic k of type integer and is given a default value of 2. X is standard logic vector 2 to the power k minus 1 down to 0. So this is the notation for raising a number to another number in VHDL, okay. So for example, p to the power q looks like this, okay, is p to the power q. Just a way of notating or describing this, okay. So S is a standard logic vector of size k, so k minus 1 down to 0, and y is a single line, okay. What are we creating again? We are creating this mux where there are k select lines and there are how many inputs? This goes from x0 all the way to x 2 to the power k minus 1, okay. So this is of size 2 to the power k and a single bit output y. So let's write the behavior in a generic way, okay. So this is a behavioral description using high level constructs. Now we are using some library functions from IEEE standard, numeric standard. We are using functions from this library to make the description more succinct. So y is assigned x, and what is the index? Is just, it depends on s. So when s is, for example, 0 0 1, this is y is equal to x1. When this is 1 0 0, y is assigned x4, and so on. So we have to convert the value of s into an integer because the index, the array index can only be an integer in VHDL. So we have to use this toInteger function. We have to first convert the standard logic vector into an unsigned value and then use a toInteger function, okay. Now this is a high level construct that we directly use from the numeric standard library, and many synthesis tools will be able to recognize this and automatically synthesize the required hardware, and the simulation will also work with this. However, it does not give you a clear picture of what the hardware looks like, but since we have already studied the structure for a multiplexer, we know what a multiplexer looks like using basic gates. Feel comfortable to use this, okay, in the context of a multiplexer. So let's go on. This will get synthesized and simulated properly. It's fine to use these structures, these library functions. Here is a test bench for our multiplexer, okay. So first of all, we declare the component, the same multiplexer with the parameter k, okay, and now we have to instantiate it. So we create an instance m0 of our multiplexer. We map k to 2, so that means it's a 4 input mux, and port map the inputs to a signal called x, where x is a vector of size 4. This is the x. We declare a signal of size of 4-bit wide. Then s is connected to this, okay, it's 2 bits, and y is connected to an output y in the test bench. Then we assign some value to x and s, and we see what y is, right? So s takes these values, okay, and s and x take these values, okay. So this is an example for a test bench. Now in question 1 in lab 3 you were asked to write a structural description for this mux using basic gates. So how can we write a generic structural description for a n input mux, for a n cross 1 mux, for example? Or this is for m cross 1 mux, or a mux where it's just like a 4 cross 1 mux, but each input is n bit wide. Of course you can combine the two. You can have two parameters. You can have a mux where there is a parameter k, which is the number of select lines. So there are 2 raised to k inputs, and each input is of width n, and output is also of width n. So you can have two parameters in this description, n and k. This is also allowed, but we will not see this because we are just seeing simple examples. You can just combine these two and write a description of a very generic mux using these two parameters. So let's see how do we write a structural description. Okay, we need an array of gates and a specific pattern of connections. So you might ask, why do we need to write a structural description where a behavioral description will do? Okay, a behavioral description could be synthesized. So there are many reasons. So for example, you may be building a specific library of components. So for example, you may be not synthesizing it for FPGAs. You may be building your own custom circuit and you want to write the structural description. You want to write the description in terms of basic gates. That's a very common thing. It does provide a very useful use case for writing structural descriptions. Okay, so we want to describe this 4 cross 1 mux where each input is n bit wide in a structural manner. How do we do it? Okay, so let's see the circuit for the mux again. This is the circuit. So it would just be a generalization of this, right? We would just have the same repeated for each bit. So this is A0, B0, C0, D0 and Y0. Then we repeat the same circuit for A1 and so on to generate Y1 and so on up to Yn. We have just copies of the same structure. So we need to do that. Now to create these n copies, okay, we need to create these n copies of each AND gate. So n copies of OR gate and so on. So obviously it will be tedious to do it manually. Okay. So this motivates us for the use of the generate construct in VHDL, used for generating regular structures like an array of gates in a well-defined manner. So let's see what is this generate construct. Okay, it's useful for generating an array of components and their interconnections. Okay, so generate construct offers a way to create regular structures using loops. Okay, and it is frequently used along with generics. For example, if you want to generate an n input mux and it should have in copies of the same structure that we saw, right? So you have a for loop, you iterate over the parameter n and create multiple copies of those basic gates. So here is the syntax. Okay, the generate construct is a block that begins with a label, some name, unique name that you give, for parameter in range and generate, and n generate. So it is a block within which you have concurrent statements. These statements are identical to any other statement that you can have in the behavioral block. Okay, for example, y is assigned some a and b, or A is and gate. For example, these kind of statements can occur here. So this parameter is not the same as a generic one. This can be anything. For example, in Python you have for I in range something something, right? So it's the same. This could be any parameter, let's say I, and then the scope of I is limited to what is inside. Okay, I cannot be used outside this. The scope of I is limited to this. So let's see an example. You want to do a bitwise AND. Okay, so what is a bitwise AND? You have inputs A0 to AN minus 1 and B0 to Bn minus 1. Okay, and you want to do a bitwise AND operation. So this is 1, this is 1, and so on. So this is A0 and B0, A1 and B1, and so on. And let the result be called, this result will be another vector of size n, and let's call it C. So basically C is A and B, bitwise AND operation. So Ci is Ai and Bi over all i's. Okay, so it's a bitwise AND operation. This is what we want to do. So let's see how to build that. Okay, we need to use the generate statement. So we need to create an array of AND gates. To each AND gate we need to connect the inputs Ai and Bi and connect that to the output Ci. For I going from 0 to n minus 1, we need to create these n AND gates. Okay, so we give some name, let's call it AND array. For I in, we don't write the word range. Okay, range is just substitute the value of range. So it goes from n minus 1 down to 0, generate. Then we create a component. So we are not going to provide an index. For example, we are not going to say AND gate I. We are not going to, this is not to be done. You have to just give it one identifier, one name. Okay, this is the name of the components that you will be building, where each AND gate instance would then be called AND underscore I0, AND underscore I1, and so on. So AND I is an AND gate to which you port map AI, BI, and YI. Straightforward. Okay, so this is an example of the generate construct, very useful. We have just generated an array of AND gates and done their interconnection using just one loop, using just one statement. So it's essentially a loop for creating regular structures. So here is a complete example. Let's define an entity called bitwise AND, where the bit width of each input is a parameter n. Default value is 4. So it has two inputs A and B, each of size n minus 1 n. So it goes from n minus 1 down to 0, and similarly y of size n. And basically y is the bitwise AND of A and B. So the structure, we want to write a structural description. We declare this component, a basic 2 input AND gate. We use it as a component. Let's assume that this is described somewhere. Okay, and we have to create an array of these AND gates. So we create an array, AND array. For I, we don't have to declare this I as a signal. Okay, it's not a signal. Is just a variable which is used within this generate loop. It is defined within this generate loop only. It's an index for this generate loop. So I in n minus 1 down to 0, generate and generate in the name. What do we generate? We generate an array of these AND gates and port map them to AI, BI, and YI. So here are the simulation results for this. Okay, after writing an appropriate test bench. So A increments, okay, and B also increments after a longer interval. So why should be a bitwise AND, right? So when B is 0, all zeros, the output is all zeros. Okay. When B is non-zero and A is non-zero, then we get some output. So here B is 1. That means B is the vector all zeros and only the last bit is 1. You AND it with anything, you are only going to see the last bit of that input A. Okay. Everything else is going to be 0 in the result, and you are going to only see the last bit of A, the least significant bit of A. So accordingly, A goes from 0, 1, 2, 3, 4, 5, 6, 7 and so on, and the least significant bit alternates between 0, 1, 0, 1 and so on. So that's what we see. Now in the next example, B is 2. So B is 1, 0. So we are only, at the output we are going to get something which is all zeros, then something, and again 0. This is the second bit in A. So if you examine this, is what we get. Okay, this bit alternates between 0 and 1 after 2 changes to A. So we get 0, 2, 0, 2 and so on, right? And now we enable, this is 1, 1 and so on. So this is as expected, the output is as expected. So you are encouraged to try writing this test bench and run this particular example to see if you get similar results. So try running this example. Okay, this is a building block to using the generate statements or the generate construct. Now, sometimes you may want to build regular structures with some exceptions. For example, let's say you want to build an array of, you want to build a bitwise AND operation. For all bits AI, BI, YI, except for the 0th bit, which is a OR gate. Y0 is A0 and B0. As an example, you want to do something different for I is equal to 0, and for all values other than 0, you want to do something same. You want to take this action, or you want to build a OR gate when I equal to 0. So you want to do some such thing. Okay, you want to build some variations into that loop, and this can be done using if generate construct. So there is a if generate construct which is available. Okay, this is a conditional generate statement, and it is usually nested within a for generate statement. Okay, it's used for accounting for irregularity. Okay, note that in VHDL there is a if generate, but there is no else, else if, etc. Okay, so let's see an example. So let's see this example. First we have the normal generate array. Okay, so AND array for I in n-1 down to 0 generate and n generate. So this is the outer array, and in this we have two conditions. So the first bit is if I is 0, and other than that if I is greater than 0. So let's see the syntax. The syntax is similar to this generate statement. So there is a label, some name, and then there is a if condition generate. So if expression generate, okay, and n generate the name. So the syntax is very similar to the outer loop. So we have one for the lowest bit and the other for the other bits. Okay, so lowest bit, if I is 0 generate, we generate a OR gate. So yi is assigned ai or bi. We are not creating a OR gate as such. We are not instantiating a component. We are directly connecting. We are writing a behavioral description. Okay, here. And for other bits, we are actually instantiating an AND gate. So this is like a mixture of behavioral and structural statements, and it's all right. We could have instantiated an OR gate here and declared it as a component. Okay, so this is the outer generate construct, outer generate block, and inside this we have two if generate blocks. If I is equal to 0 and if I greater than 0. Okay, so these are the conditional generate blocks. Pretty useful. So let's move on. Here is a simulation result for this bitwise AND operation. Okay, this is the same description, and you can just verify that the output is as expected. Okay, so when the input B is all zeros, Okay. The output is not all zeros because one of the lowest bit is an OR operation. So when this is 1, for example, we have a 1 and so on. We have alternating ones, right? Why? Because we have A0, B0 being ORed together to get Y0, and for all other indexes we have AI, BI connected to an AND gate to give YI. So this is the hardware that's being simulated, and this is the result as expected. Let's see how we can use this generate construct to write a structural description of a 4x1 mux with n-bit inputs. Okay, so this was the earlier circuit, if you recall. Now what we have is, we have this thing, this portion replicated for each bit position. So first we generate Y0 using A0, B0, C0, D0. Then we replicate the same circuit to generate Y1 using A1, B1, C1, D1 and so on. So effectively what we have is a 4 input mux with inputs A, B, C, D, each of size n, and an output Y also of size n, and 2-bit select line. If the select line is 0, 0, then A is connected to Y. If 0, 1, B is connected to Y, and so on. So we are building a structural description of this mux by instantiating an array of these gates. So let's see how we can do that. Okay, so let's first declare the entity for the mux. You have n as an integer. This is the bit width of each input, so default value is 8. So each A, B, C, D will be by default 8-bit vectors. S is 2-bit again because we are just selecting one out of 4 options, and Y is again n-bit. Okay, and now we want to write a structural description, so we need to have these components: 3 input AND gate, 4 input OR gate, and a NOT gate. Okay, let's assume that this behavior is described somewhere. This is just described. Okay, and now we need some signals, right? So first of all, we need the complemented versions of each select line. So let's call it not S. So there is not S1 and not S0, initialized to all zeros. First, we need only 2 of these NOT gates. Okay, once you have S1 and S1, not S1. Similarly, you have S0 and not S0. These can be used as inputs in all of the subsequent gates. You don't need more copies of these. Okay, the same signals could be used, so we don't need to have this within the generate loop. Now let's have the generate loop, where we are going to replicate this structure of 4 AND gates n times. Okay, so recall the description that we had in the earlier example. We just put it in a loop. So let's give it some name. Let's say output bit I. So this is generating the circuit for bit I. Okay, so this is generating finally yi is, and now we iterate over I going from n-1 down to 0. We declare a signal in this scope. So note that generate is a block that begins from this label to end generate, and within it you can have declarations. So to have declarations, you add a begin and put whatever declarations are there before this begin block. Okay, so this becomes the body of the generate block, and anything that happens before that are declarations. So we declare a local signal called OR in for collecting the outputs of the 4 AND gates together. So this is called OR in. Okay, and what do? We have these 4 AND gates. We connect different values of S, either complemented or original, to this. We connect each of these inputs AI, BI, CI, DI. So for I equal to 0, we are only connecting A0, B0, C0, D0. Then connecting all their outputs together to an OR gate, and finally generating Y0. So at the end of this, for one value of I, you are combining AI, A0 up to C0, A0 up to D0, and generating Y0. Similarly, for I equal to 1, you are combining A1 to D1 and generating Y1. Okay, so this is a local, the signal has a local scope. There will be multiple such copies created for each iteration of I. Okay, so essentially we have n copies of this block. So this is a very useful construct. Imagine if we had to do this manually. We could not do it for an arbitrary n anyway, right? We had to fix n to write a structural description. So there was no other way of doing this without using generate constructs. This is a very useful construct for writing regular structural descriptions. So let's come to the exercise for this lab. Recall that in lab 2 you built a 4-bit ripple carry adder using 4 full adders. This was the circuit. You connected 4 full adders. Full adder is a circuit that adds 3 inputs A, B, carry in to produce a sum and a carry out, and we had 4 of them chained in this manner to produce a 4-bit adder. Okay, so the final ripple carry adder has input vector A of size 4, B of size 4, and finally a sum of size 4 and a carry out and a carry in, right? We had this circuit. Now we want to generalize it to an n-bit adder. So we need to instantiate a chain of n full adders using the parameter n defined as a generic parameter and using the generate loops to instantiate n such full adders and to connect them in this manner. That is the first question. Okay, so you are required to write a structural description of a n-bit ripple carry adder using n full adders as components. So n is the generic parameter. You need to use generate loops to instantiate this chain of full adders and use the same port names as the last lab. However, the width of these, for example, is still a ripple carry adder with the same name. It has inputs A, B and sum, but now the width of them is n. Their width is n. Okay. You need to write an appropriate test bench and see that it works and submit this code in a single file. Notice that for all the labs, you should not submit partially written code or code that does not compile or that does not produce the expected results, because this will be considered as malpractice. So if you cannot solve a particular question, don't submit its solution. Submit the solutions for all the questions that you can solve fully. Okay, so here is an interesting question. So once you build this ripple carry adder, how do we use this to perform both addition and subtraction? Okay, subtraction, by subtraction we assume this is signed 2's complement form. So let's see the component that we have. This is your ripple carry adder. This has an n-bit input A, an n-bit input B, and a single bit carry in. Okay. Then we have a single bit carry out and an n-bit sum. So this is the final ripple carry adder. Can this be used to perform both addition and subtraction? So recall that x minus y is the same as x plus 2's complement of y, right? So we want to build a circuit that can produce x plus y as well as x minus y depending on an operation select bit. So let's see what the question is. You are asked to write a structural description of an n-bit adder-subtractor module that can either perform signed addition or signed subtraction based on the value of a op-select input. That is, if op-select is 1, then inputs A and B should be added together to produce, let's say, y is equal to A plus B. If op-select is 0, and if op-select is 1, it should produce A minus B. Okay, the results being in 2's complement form and the inputs also being in 2's complement form. Okay, So let's see how this can be done. So we need to use our ripple carry adder as a component. Okay. We further need an array of inverters and some multiplexers. Okay. So essentially we want a circuit that can add two n-bit numbers. So A is an n-bit input, B is an n-bit input. Okay. And then it produces an output Y, n-bit output, a carry out. Okay. Because adding these two numbers could give a carry. And then in addition it's asked, of course you need an op select input. So if op select is 0, then Y is A plus B. If op select input is 1, then Y is A minus B. And note that A and B are represented in 2's complement form. So either A or B could be positive or negative numbers. So both could be positive, both could be negative, or one could be positive, another could be negative, and so on. So all combinations are possible. So A and B could be any kind. They could be positive or negative, and the op select could be 0 or 1. If op select is 0, you produce A plus B. If it is 1, you produce A minus B. And notice that you are asked to provide an additional output called overflow. Okay. So overflow indicates if there was actually an overflow. That means if you added two positive numbers but you got a negative result, can that happen? So for example, let's see 4-bit numbers. You are adding 0, 1, 0, 0, 0, 1, 0, 0. Okay. In 4-bit representation, the highest bit is 0, so this is a positive number, which is plus 4. This is also plus 4. When you add them, okay, what you get is this. If you interpret this in signed 2's complement form, this is 1, so it means it reads as a negative number, right? So what is this? This is minus something, right? What is it? So let's find the 2's complement of this. This is 0, 1, 1, 1, and let's add 1 to it. So this is 1, 0, 0, 0. So this is actually minus 8. That's incorrect, right? We should have got positive 8, but positive 8 cannot be represented using 4 bits. Okay, so this overflow bit indicates that we got a result that cannot be represented using these 4 bits. Okay, so overflow bit is 1 if both the inputs were positive but the result was negative, or if both the inputs were negative but the result was positive. So essentially you examine the most significant bits of the two inputs, that is A n minus 1, B n minus 1, and the sum n minus 1, and based on these 3 bits you either set the overflow bit or you keep it 0. If there was no overflow bit is 0. So you are asked to work out the logic for this overflow output. Okay, so essentially if you add two positive numbers but get a negative result, or if you add two negative numbers but get a positive result. Okay, and in addition, so that's for addition, right? What would be the logic of the overflow similarly for subtraction? If A is positive and B is negative, then A minus B is positive and positive, so you should get a positive result. Similarly, if A is negative and B is negative, then you should get a negative result. But if you get a positive result, then overflow bit should be set. So you are asked to work out the logic for the overflow bit. Okay, and then write an appropriate test bench for this. So let's see what the hardware will look like. First of all, what should be the interface of this adder-subtractor module? Let's call it adder-subtractor. It has a generic parameter called n, and therefore it has a n-bit input A, an n-bit input B, an n-bit result Y. It has an op select input of 1 bit. If op select is 0, you should have Y is equal to A plus B. and if it is 1, y should be equal to a minus b. Okay. And what else? We have a carry out, and an overflow bit. Alright. How do we construct this? What should be there inside? So obviously you are asked to use a n-bit triple carry adder, right? Remember, our n-bit triple carry adder could only do addition. So how do we do subtraction? We need a multiplexer, right? So this is a n-bit triple carry adder. It had inputs input A, B, carry in, Y, and carry out. So to A we connect A, and to B we could connect B if op select is 0. Then Y would just be a plus B, and carry in will be 0, right? We don't want to carry in. So again we have another mux here. So if op select is 0, then we don't give any input to carry in, and Y would then be a plus B. But if op select is 1, then what do we connect here and what do we connect here? Okay, we could either connect 0 here and have 2's complement of B here. So if op select is 1, then we take A and we add to it 2's complement of B to create Y is equal to A plus 2's complement of B, which is essentially the subtraction A minus B. But 2's complement involves an addition, right? 2's complement is actually inverting all the bits of B and then adding a 1 to it. So again you need to add. So instead of that, what we do is we add that 1 here, right? So we add that 1 and we just do a bitwise not. So let me call this B bar. B bar is actually bitwise not of all B basically. Okay, so this is what we do, right? So let's just see, let's have an array of inverters here, so on to get this B bar. So essentially this is the input A, this is the input B for the outer box. Okay, so this is Y as we need it, this is carry out as we require. And how do we set the overflow? Overflow depends on some bits of A, some bits of B, and some bits of the sum, correct? So we need to have some logic here that takes in bit an minus 1, bn minus 1 and the sum here, and sets the overflow bit. So this is essentially using the same ripple carry adder as a hardware and adding some extra multiplexers and some logic here, we are able to build a programmable adder-subtractor module. So depending on op select value, this hardware could perform addition or it could perform subtraction. So that's a useful way of thinking. Okay, so multiplexers are a very useful building block, and this example shows how you could build such a circuit using some multiplexers. Okay, so you are asked to write the description, use the n-bit triple carry adder described in the previous question as a component, use 2x1 multiplexers as components, and then finally write a structural description of our adder-subtractor module. Okay, it should have these outputs called carry out and OV in addition to the output Y. You are supposed to write an appropriate test bench, test if it works, and submit all code as a single file with a different name, question 2. Okay, so see you for the next lab. Bye.